Hello, everybody. This is a video of what we did in class today pertaining to fission, fusion, and binding energy per nucleon. So here's the worksheet we did. If we calculate the binding energy of any nucleus, you can divide by the number of nucleons. So binding energy per nucleon is literally just the total binding energy divided by the number of protons plus the number of neutrons, otherwise known as the number of nucleons or the mass number. That's this top number here, you might remember. So if you do that for neon, you calculate it, divide by 20, you should get this number. You do it for calcium, you get this number. Notice it's more negative, which means it's more bound. Notice that if you do it for iron, it's even more bound. What you do is you add up the number of protons, right? In this case, it would be 26 protons times the mass of a proton plus 30 neutrons times the mass of a neutron, right? And then you subtract this mass of iron, and then you multiply that by C squared, and you get the binding energy of iron. If you divide by 56, you average it over each individual nucleon. Now, the reason why that's important is because we want to find the average per nucleon to compare iron with calcium, to compare iron with any other element. I just chose platinum as a somewhat random example. If you do it for platinum, you're going to get 78 protons and 105 neutrons. You use the binding energy formula. You divide by 183, you're going to get negative 1.272 something times 10 to the negative 12 joules per nucleon. 272, I got a 4 there. Notice that that's similar to neon. Notice that the binding energy grows in magnitude to iron and then becomes less negative past iron. If we did this for all of the elements, that's exactly what we would notice. So what we want to do is we can actually graph this. And if we graph it, we get this graph right here, where we start out with 0 binding energy for a single proton. It's bound to nothing. So the binding energy of hydrogen 1 is 0. And then at helium-4, all of a sudden it plummets to a very negative value. Now, you can ignore this vertical axis. That's mega electron volts. It's just another unit of energy that's useful on a particle level. I'm sorry that this is not in joules, but the shape is what's important. Notice that there are dips at helium, carbon, and oxygen, which makes them stable. So it's energetically beneficial to go downhill to more negative binding energy. Why? Because larger binding energy per nucleon means what? Means more bound. What does that mean? It means that when it forms, more bound means there's a clap when it forms. And that clap releases energy. So that means it's energetically beneficial for it to occur, for it to form. Right? So you're going to need energy input no matter what, but for instance, to push protons together takes energy. But if they actually stick together, you get more energy out than you got in. And then that energy can feed a new chain reaction. So it also shows stability. So helium will not spontaneously decay into anything. Neither will carbon or oxygen 16, carbon 12, helium 4. Those specific proton-neutron combinations are stable because they're in these wells. It's like a ball in a bowl. Iron is very stable. nickel 62 actually has the largest. Iron 56 also has a very large binding energy, meaning more negative, large magnitude per nucleon. So if we notice, we get more negative down to iron and then less negative, which means if we fuse smaller objects into iron, they clap together, which is the answer to this question. They will clap together. Explain why, if a nucleus of smaller binding energy per nucleon splits into two more nuclei of larger binding energy per nucleon, energy is emitted fission. Explain why, if two smaller ones connect to combine to make a larger one, it releases energy. Well, that's because if I have two smaller ones that are less bound, less binding energy per nucleon, and they fuse into one that has more binding energy per nucleon, more meaning more negative. That means there is this clap effect. I hope the clap effect makes sense. There is this activation of the strong nuclear force, which claps this together. More bound means that the strong nuclear force activates itself. It literally pushes it inward. So more bound, I would write this down along with this picture. More bound means Fs nuclear activates a clap, a bringing together, like a smashing of magnets or a smashing of two cars or something. And that means that energy is released in that clap. Right? Remember, we've been over the clap. You can see my other previous videos on that. Right? So the point is we want to connect this physical mechanism, which we already know, to the concept of fusion and the concept of binding energy per nucleus, informing us whether or not we get this clap or not. Now, here's the thing. If I have a big nucleus that's less bound, it doesn't matter if I start with something big or small. What matters is I start with something more bound than what it turns into. If I start with something less bound, less binding energy per nucleon, and it splits into two smaller pieces that are more bound, and if you remember, what causes something to be more bound is a combination of three things, right? We have the electric repulsion, fighting to make things fly apart. That is large range through the nucleus. We have the strong nuclear force is a small range. And we have the Pauli exclusion principle, which says that if you have too many neutrons or too many protons, but too many protons, the electric repulsion really dominates that. Too many neutrons, they fly apart. It's a repulsion. Two things can't be in the same place at the same time, is what this says. So ultimately, that makes iron most bound. So that means this, say this is larger than iron, or larger than nickel 62. Say, we'll just use iron as our example. Say this is uranium, plutonium, iodine, anything on the periodic table, radon, any one of those big nuclei. What's happening is the electric repulsion inside of it is trying to push it apart, and it eventually does. The Pauli exclusion principle says too many neutrons, it's trying to push it apart. And the strong nuclear force, which only has a small range, can't do it. It can't reach all the way out to hold it together. So it splits. It's called fission, whereas our previous example is called fusion. Fission will release energy when the products, these, are more bound than the initial nucleus. So these clap because they're smaller, so the nuclear force can now activate And it says, oh, the strong nuclear force can now do its thing. Goes clap, boom, it's a boom. Right? Clap your hands. Like the electric repulsion here was pushing this big nucleus apart. When it splits into two smaller ones, the two smaller ones are like, it's like the Wile E. Coyote, like, I got nothing keeping me up. And it just, boom, they clap together. These two smaller ones clap together with a huge amount of force. Boom, and that's the energy release. So when you end with something with more binding energy, more bound, whether it's fusion or fission, the strong nuclear force activates. Whether it's fusion or fission, if you end with more bound, the strong nuclear force activates a clap and energy is released. Boom. Tomorrow and in the next video, we're going to look at this mechanism in a little more microscopic detail to ask, well, what type of energy? What does it mean to say heat is released? What does it mean to say energy is released? Something has to carry the energy. What is it? We're going to find that out. That's next video. Don't worry. Pause this, see if this makes sense. This is the picture of fission and fusion. These are the answers to these questions. Let's do one numerical example. So if we go up, so these are the answers to these questions. See if you can answer the back page. You notice that fission releases energy coming from this side, bigger than iron, closer to iron, no matter what it is. If I start with uranium and then with bromine, I'm going to get energy released because this is more bound than what started it. If I start with carbon and form oxygen, that's more energy released. If I start with oxygen and go to iron, go to neon, calcium, iron, I get something more released, right? So that is the picture we want to tell today. So if we look at the binding energy per nucleon, we see that iron is most bound. And from the comparison, this is the whole point. How does binding energy per nucleon help us tell the significance of this? It tells us if we're more bound or less bound. And it tells us, therefore, if energy is released or not based on the notes we just took. So what would happen if two neons fused into a calcium? Well, I look at the binding energy per nucleus. I notice that the neons, 20, that's 10 protons, 10 neutrons, 10 protons, 10 neutrons, they are less bound, less binding energy per nucleon. And the calcium is more bound. Now, if we actually added up the masses, like you've done, if you actually added up the masses for neon, and calcium from the table that's just above here, you would see that there's less mass on this side, that the calcium has less mass, which means energy is released. So you can look at this from two different angles, and please do. More binding energy per nucleon as the result means energy is released. Less mass is because of that. More binding energy, as we know, means less mass, right? More negative binding energy takes away mass. That means the energy got released in a clap, right? There's this compression. The strong force is activated here. The electric repulsion isn't enough to overcome it yet. It's not too big of a nucleus. Calcium is a nice, tight, strong nucleus. Boom, it claps together, which makes it fly in a direction, boom, or it releases probably a photon, maybe another particle. We're going to look at what it's actually released in it tomorrow. The point is there's excess energy because it's more bound. Now, if I tried to take that same calcium nucleus and split it apart, if I tried to do fission with it, it wouldn't work. Well, it could work if I could put in the energy, neon. I would have to input energy. It's the same, but in reverse, right? So I could figure out the output of energy by looking at the delta mass times the c squared. I could also figure out the energy released by looking at the change in binding energy times the total number of nucleons through this. That's pretty cool. right? So either way, I can calculate the energy released. That's the same as the energy input, delta MC squared, but I have to add it here. It's negative. It's reduced, so energy's output. So why? Well, these are less bound. If I try to take these apart, it's literally overcoming the strong nuclear force to make something less bound requires energy input. These nucleons are farther apart from each other than in the calcium nucleus, right? In the calcium, they're tighter together, where in the neon, they're farther apart. So I literally had to take them apart, and that lost energy. That required energy input to force those nucleons apart. So that's the answers to those. And this tells us everything about whether it's exothermic or endothermic. This is endothermic. This is exo. So you only have a fission release energy when it's down to iron. You only have fusion release energy when it's up to iron. So let's do one more. I anticipate a bell soon. Don't be freaked out. Let's do number 5. You can do number 3 and 4 on your own if you wish. Let's do number 5. So plutonium decays into an alpha particle, which is just a helium nucleus, and osmium 179. So we write this like this, right? We say 183 plutonium decays into 179 osmium plus a helium nucleus. Well, if we add these masses up, we see that these masses equal 3.037365 times 10 to the negative 25 kilograms. Just add those two numbers up. And this one equals 3.037438. You might notice that though it's very similar, 3.037, this is less mass, which means this is more bound. Notice it's closer to iron on the periodic table, right? 179 is closer to 56, which means it's more bound. Why is it more bound? What does that mean? It means that the electric repulsion is less. So the strong force activates. It can do its thing, right? There's fewer neutrons, so there's less Pauli exclusion principle too. Fewer nucleons in general, but fewer neutrons, right? So more bound means these things, which means it claps. Strong force activates, right? So the electric repulsion was trying to push this apart. It actually did, but this section of it maintained itself, boom, clapped together a little bit and released an energy which is going to equal delta M times C squared. I'm sorry, I didn't actually calculate the difference too. You just have to subtract this and this, multiply by C squared, 9 times 10 to the 16, and you have your energy released. Tomorrow, we're going to see that most of that energy is actually in this helium that flew out at a very high speed, like a catapult. We're going to make sense of that. It's just conservation of momentum. You have a heavy thing and a light thing. What takes most of the energy? The light thing. That's it, everybody. I hope that made sense. Ask questions. Stay tuned for tomorrow. Have a beautiful day, friends.